tangent line to a circle theorem. What we have here is the theorem is an if and only if statement. So we have to prove it in two directions. One direction and then the other direction. It's if and only if. So what does it say? It says that line L is tangent to circle C at D. So it's tangent to circle C at D. This is the point D right here. This is D, let's say, right? This is where they're tangent, right? If and only if line L is perpendicular to the segment CD. So what you have here is that it looks something like this. This is the segment CD, right? And both directions are true, like I said. So the one direction, right, is if line L is tangent to circle C at D, I'm leaving that part out, then line L is perpendicular to CD. So in this case, we're given it's 100% true. It's always true. No assumption, no nothing, just that line L is tangent to circle C. So then that means that there's this one point where that they share, that point D. L shares D, D is on L, and D is on this circle. Now what I need to prove is I need to prove that L and CD, this line, are perpendicular to one another. And the way you go about doing that is that you assume that the conclusion that they're not perpendicular. You assume that the conclusion is false. So assume L is not perpendicular to CD. And what that allows is well, we're assuming that it's not, which means that there has to be some other line, right, from C to L that is perpendicular. That's a postulate. C is a point off of line L. And through every point off a line, there exists another line through that point C that is perpendicular to L. And there's exactly one. That's a postulate. Okay? So what you have here is that then if we're assuming that CD is not perpendicular to L, there has to be some other point M where the line joining C and M is perpendicular. So then that forms your right angle. So if we assume L is not perpendicular to CD, then there must exist some CM with CM perpendicular to L. Okay? Now, with this, now let's start remembering, right? We know for a fact that line L is tangent to circle C. What does tangent mean, right? A line is tangent to a circle if they meet at exactly one point. So we know L and the circle meet at exactly one point. That's point D. Okay? So then that means that this point M cannot lie on the circle, and it has to lie outside the circle. So since L is tangent with circle C at D, and only at D, right, then M lies outside circle C. And now we just need to convince ourselves that any point outside the circle is further away from the center than any point on the circle, right? That's the statement. I'm not going to write it, okay? But you should really convince yourself that any point outside the circle, this point, it's outside the circle, right? Whatever, point Q, it's for sure further away from C to Q, the center of the circle. From C to Q is further away than from C to any point on the edge. So since M lies outside the circle, you know that CM, the distance between C and M, is greater than the distance between C and D, since D lies on the circle. Okay? And then we're going to say something else now. Now, if we look at this triangle here, so look at the triangle that was formed, the triangle CMD. So, triangle, we could say, however, triangle CMD is a right triangle. And since it's a right triangle, it has to have a hypotenuse. And if you look, the hypotenuse is opposite the right angle. That's CD. So CD is the hypotenuse in this right triangle. That makes CD the longest side in this triangle. So then that means that CD is greater than CM. And this is your contradiction. Because I have it that CM is greater than CD, but then now I have that CD is greater than CM. Both of these things cannot be true. You say, this is contradiction. And you could draw these two arrows facing each other to illustrate it's a contradiction. And that contradiction arose due to our assumption. And we got a contradiction by making this assumption. Therefore, our assumption must be false. Thus, or therefore, thus means the same thing as therefore, thus, our assumption is false. And what is the falseness of our assumption? Our assumption is that L is not perpendicular to CD. Therefore, L is perpendicular to CD. And we're done in one direction. You could put a nice little square box to illustrate. This means it has been shown. That symbol, that means it has been shown. Okay. I show that this direction is true. Now let's show the other direction being true. So now in this one, I have that L is perpendicular to CD. So I just have this point D, right? And I'm going to have to change this diagram a little bit to modify it for our assumption. So I know in this case that this is a right angle. CD, line L and CD are perpendicular. Okay? I want to prove that L is tangent to circle C. And just like in the other one, here's line L. Just like in the other one, I assume the conclusion is false. I get a contradiction, which means that my assumption, I assume the conclusion false. I get a contradiction, which means that my assumption is wrong and the conclusion is true. Okay, so replay that over and over. Make sure you see how a proof by contradiction works. That was a quick summary of how a proof by contradiction works. So I'm going to assume my conclusion false. Assume line L is not tangent. It's not tangent. Not tangent to circle C. Okay? If it's not tangent, okay, what that means is that this line, right, L, is not tangent. It means that it intersects it twice at some point D and then some other point. I'm going to try and modify this. So let's see if I can do this. Okay, so I'm just going to move everything over, and then I'm going to move this back over to D. All right, I'm going to have to change it again, but that's okay. Let's see, so try and do that. And then, so if it's not tangent, then that means that L, right, I'm assuming L is not tangent. That means that it intersects the circle at D and some other point M based upon my assumption. Okay? So again, L, I'm assuming, this is L now, I'm assuming L is not tangent. It is perpendicular. Line L is perpendicular to CD. Okay, so this is CD right here. And they do form a right angle. but I'm assuming it's not tangent. Tangent means that it hits it at one point. Okay? Exactly one point. So if it's not tangent, that means that L either doesn't hit it at all or it hits it twice. We know that L hits the circle at least once at D because of this fact. L is perpendicular to CD. So CD is this radius, right? And we know that it's perpendicular, so it has to hit at D, this line L. And since it's not tangent, then the only other option would be that it hits it twice at some other point M. Okay, so again, assume line L is not tangent to circle C. This means there exists some point, some other point, M, some other point M with where that some other point M that is on both L and circle C. Okay, so M is on both line L and circle C, and so is D. Now if we look at this picture again, and let's just go through the logic of how this works. So I have it where CM is now a radius. It's from the center to an edge. M lies on the circle. So if CD is a radius and CM is a radius, right, they must be congruent. CM is congruent to CD, or that the lengths are equal. Let's write it as lengths. So CM is equal to CD, since they are both radii. Since they are both radii. Okay? Now, after that, we're going to get the contradiction part of this. Let's look at this triangle again, right? Triangle CDM. However, right, triangle CDM is a right triangle with CM as hypotenuse. Therefore, right, so therefore the three dots means therefore, CM, the distance from C to M must be greater than the distance from C. But wait, because it's the longest side in this right triangle, right? It's the hypotenuse. CM must be greater than CD. This is a contradiction with the fact that these two were originally equal. This is a contradiction. And this contradiction arose due to my assumption. This is a contradiction. Assumption must be false. The assumption is false. My assumption was that line L is not tangent. And L is tangent to circle C. Okay? To circle C. To circle C. And you're done. That's it. And again, you can put the, just know you've proven the theorem in both directions. Okay? And you're done at this point.